with appropriate given values, but your mastering chemistry that's due on Friday night is a more immediate need for that. Okay? Let's spend the rest of our 8 minutes here talking about how to determine the strength of something just based on its structure. Not even so much how to determine, but if we know the trend, why is that? Okay? Being able to rationalize a difference in acid strength. Okay? So, for instance, the biggest one that we can probably think of was the difference of HF and HCl. Okay? The chloride, bromide, iodide, those make strong acids, but HF is a weak acid. So, let's start by considering the size of the F atom versus the Cl atom. What happens to atomic size as you go down a column?
Small.
We build on an additional shell of electrons each time we go down. Okay? So if we were drawing this to scale, it might be something like H is about the smallest, F, something like that. Pretty small, though. H. Cl is an additional shell of electrons pass beyond what fluoride has. Okay? So now, HF is much closer together, right? If we have a bond length there, it might be something like that. Okay. All right. So if those are their bond lengths, think of Coulomb's law. Right? Coulomb's law is the attraction of oppositely charged particles. Which of those will be the stronger bond, the HF bond or the HCl bond? The shorter one. Okay? Coulomb's law says that as opposite charges are brought closer together, they become a stronger attraction. Right? So H.
Like a cube root function?
No, that one's linear. The radius is on the bottom of Coulomb's law, but the two charges are on top. So that's where the square and stuff comes from. Okay, but shorter bond length, stronger Coulomb's law. Okay. All right. So what does that have to do with the strength of an acid? Why is HF a weak acid and HCl is a strong acid?
Because fluoride doesn't share well with others. It's greedy.
So part of the confusion comes between the use of stronger bond versus acid strength. Okay? To have a strong acid, do we want a strong bond? No, we want a weak bond. That's a strong acid. Okay? Strong acids have weak bonds. That's what makes it a strong acid. We were talking about that a little bit earlier. If something is a strong acid, that H just kind of falls off and just flies away. It's not strongly attached to the other atom. Okay? Simply because HF is such a small bond length. Okay? F is unusually small, okay? Especially because size decreases going to the right, because we have more protons and more electrons within that shell. Okay, so fluoride is unusually small, and it forms an unusually strong attraction to that H, which means it doesn't want to give it up as easily as the other ones do. Okay? So let's make a little, this is the next column over, okay? Oxygen, sulfur, selenium, and tellurium. With this idea in mind, we should be able to pick out the strongest acid here. What do you think?
So it should be
Yeah, tellurium. Yeah. So our trend would go something like that.
And that is trended acid strength?
Yep. Of those. Okay. But it's the opposite trend in bond strength to H, correct? Okay. Because the H tellurium bond is much longer than the other ones there. Okay. But for the same reason as we saw before. Okay. So bond length is the key determiner when looking down a column. Okay. Longer the bond is, the weaker it is, the more the H will just fall off. Okay. Different idea when you're going across a row. Okay. Why is H2S a weak acid and HCl a strong acid? They're in the same row. Okay. It goes sulfur then chlorine next to each other. Okay. This comes from electronegativity, going across a row. So which is more electronegative, sulfur or chlorine? Electronegativity. What's the most electronegative element?
Fluorine.
Yeah. Fluorine is the most electronegative. So electronegativity increases going to the right. It increases going up. Okay. So the more electronegative one here is chlorine. Periodic table. There we go. Electronegativity increases going that way, increases going that way. So we were comparing those two. Okay? All right. Let's draw an HS bond and an HCl bond. Okay? You said that chlorine is more electronegative. That means this bond will be more polarized, partial negative, partial positive, less so over here. Okay? In which case is the H closer to already being an H plus? It's a neutral H in these compounds because it has its own electron and it's sharing an electron from the other one. Okay? But removing, if something is strongly pulling the shared electron density away, the limit to that is completely removing both of those and we're left with an H plus. Okay? So the one that's more electronegative is closer to already being an H plus. Okay? This H is more plus than this H here. Okay? Another way of saying that is that this bond is more polarized. Okay? So, if an H already has those electrons mostly removed from it, it's much easier for that H to just fall off and become an H plus. Whereas over here, the H is sharing a more significant amount of those electrons to it. Okay? So, that's why the more electronegative the atom attached to H, if we're going across a row, okay, size is no longer nearly as important going across a row. The size is more similar. Okay? Now it's electronegativity. Okay? So this is the row above it. HF, H2O, H3N, CH4. Which of those would be the strongest acid? Which of those has an H that's the most ready to leave? Yep. So let's do that. Most polarized bond. HX bond makes for the strongest acid.
Which is still a weak acid.
Yeah, it's the strongest of these. But in the case of that row, those are all very short bonds, so even the strongest of those is still considered a weak acid in general. Okay? So we consider that a weak acid. This is amphoteric, right? Could be an acid or a base, depending on the solution. We usually call that a base, okay? And we don't really even talk about acid-base reactions of that much at all in here. Anyway, you will in organic chemistry if you take that. But. Okay. I think we better finish the rest of these next time.